Hello everyone. So we will continue our discussion about the photochemistry, and now we have talk about the mechanisms, like how to predict a mechanism in photochemistry. Now in this video, let's talk about this cis-trans isomerization. Now before comes into this photochemistry part, let's first little bit talk about the cis-trans isomerization in more detailed way, right? So let's take an example. This alkene. Here we have an alkene, so here we have a hydrogen, here we have a hydrogen. So this is in the cis state, this is on the cis conformation. Now what I am referring to as the isomerization is I'm going to convert this cis product into the trans. In trans, if you remember, we have the hydrogens on the opposite side. This is the trans product, right? Now in order to go from here to here, from our basic organic chemistry knowledge, let me draw it individually, let me draw it separately. Okay, let's take this molecule here. This is the alkene, so this is the sigma bond. Okay, I hope you know this is the sigma bond. Now there are two p orbitals. Let me draw it in red color like this. This is the two p orbitals which have interacted with the which is interacted to each other like this manner. Okay, this is the pi bond. Now here we have the cis. Now in order to obtain the trans, right, in order to obtain the trans, you need to rotate this part of the molecule like this while holding this part still, right? You do not change this part, you only rotate this hydrogen to here. Okay, so you just need to rotate this particular bond in 180 degrees. Now just imagine this, right? So when you rotate this from here to here, you will see this these two p bonds, these p bonds are also rotating, right? But these two p bonds, these p bonds, sorry, not bonds, these p orbitals are not changing, they are staying still. Only these p orbitals will be changed, they will rotate along with these bonds. Now when these p bonds are rotating, you will sense that these interactions will stressed out, right? Because these are moving, so these are stressing out. Now this stress results in the this stress results as a energy barrier. So in order to rotate this molecule to obtain the trans product, you need to overcome this particular energy barrier, because this pi bond over here, this pi bond is not letting you to rotate this. In order to rotate this, you need to overcome this pi bond, or you need to break this pi bond. With the pi bond you can't rotate it, so energy barrier would appear to overcome this pi bond in order to rotate it to the trans product. If I draw the energetics, you can clearly understand it. Here we have the cis product. Now in order to go to the trans product, you need to overcome an energy barrier. This is the energy barrier, delta E. Now we can draw this with the rotation angle theta also, so you can identify the highest energy or most unstable formation occur at the 90 degrees rotation angle, right? So we will not talk that much details into this. Just what you need to understand is, when you try to obtain the trans product, you need to rotate this particular structure, right? When rotating, this pi bond is going to avoid that particular rotation. In order to rotate into the trans product, you need to overcome this pi bond, and this process resulting in energy barrier. So going from cis to trans is nearly impossible, right? It's very hard due to this huge energy barrier, because we have to break the pi bond. But when we introduce a photochemistry into this, you will remember photochemistry has an interesting manner. What happens in photochemistry? if I take this molecule, this alkene, now this is in the cis state, this is on the cis conformation. First, what I'm going to do is I'm going to excite it. So with the light or radiation, I'm going to excite this molecule into either singlet or triplet excited state. Here we have the same molecule but in the excited state. So this is on the ground state, cis. This is also cis, but this is on the excited state. Now we have discussed what happens to this pi bond in the excited state in our previous video. If you want to know about that particular incident, like exactly what happens and how that relates to the weakening of this particular pi bond, I highly recommend you to watch this video. I have explained it very detailed manner. Now when this excitation happens, you will see when you draw the molecular orbital diagrams, which we have done in our previous video, the bond order in the excited state for particular this pi bond is lower compared to the ground state, which means in the excited state you have weaker pi bond. Now this weaker pi bond, right, this weaker pi bond can result in a reactive intermediates. It can be radicals or with another substrate, like whatever. There are reactive intermediates. Right. So for the reactive intermediates, right, for reactive intermediates, this pi bond is now broken, right? There's only sigma bonds. There is only a sigma bond. But due to this excitation, due to this weakening of this pi bond, that this delta E, the energy barrier occurred due to this pi bond initially, is greatly reduced. Now because this pi bond is much more weak, right? This pi bond is much more weaker compared to here. Here we have the complete strong pi bond. Now, but when we excite this particular molecule, right? When we excite it, we have weaker pi bond, so we can give a small energy just to overcome this pi bond interactions. So we can easily rotate this. That's the concept here. That's what you need to understand. When you excite the molecule, you can weaken this pi bond. You can weaken this pi bond. With the weakened pi bond, you can easily rotate it through this energy barrier. Now, if we consider this process like in comparable manner, here we have the energy. First, let's draw the normal process. Here we have the cis. Now here we have the energy barrier. Now it has moved into the trans. Now what happens, this is the molecule, right? This is the initial molecule. Now what happens when we excite the molecule here? This excited molecule here, this excited state, you need to remember, every time when you excite a particular molecule, it has higher energy. It is much more unstable compared to the ground state. So when we excite the molecule, when we represent the excited form of the molecule, it has higher energy compared to the ground state. This is the excited cis conformation. This is the excited molecule. Now from the cis, this excited molecule, you get the reactive intermediates. Here we get the reactive intermediates, and then from these reactive intermediates you can again form the trans product, trans in the excited state. This is the energy diagram for excited state. This is for the ground state. So when we compare the delta E values, so let me draw it, this delta E one and this is delta E2. You will see that delta E1 is much more greater than the delta E2. So when you try to do this isomerization in the ground state, you need to overcome this huge delta E1 energy barrier. But if you irradiate your molecule from initially, here you irradiate your molecule into the excited state using the photochemistry, and then you have delta E2, which is smaller energy barrier, which go through this reactive intermediate. We can denote this reactive intermediate as X. Let me draw it on the yellow color. Here we have it on the X. This is the reactive intermediate, and then in the next step we have the trans excited state molecule. Now when we think about the overall process, let's say we need to do this, we have the cis molecule, Now what we need to do is we need to convert this cis molecule into the trans molecule. Now what is the procedure? Now what you need to do? First step is to excite the molecule. First you need to excite the molecule. Here we have done the excitation. So this is the initial place, then you do the excitation. Now what happens? Initial place is here, we are on the ground state. So when the excitation happens, here we are moving to the cis. In the next step, what we do is we are going to go through the photochemical reaction process, and we are going to obtain the reactive intermediate. Or the X product. So this is the number 3. Here, this is the number 3. We go through the normal reaction to obtain the reactive intermediates. So in this place, right, the pi bond is broken, right? So in this place, this is our molecule. It's mostly a radical form. There can be variations, like, okay, this X state is depend on the mechanism and the molecule. So it can be a radical. Again, there can be substrates and stuff. Just remember, remember it by, this is the reactive intermediate. This is the transition state for this particular reaction. And then after this X, right, you can see this is the excited state reaction mechanism. This is the normal ground state reaction mechanism. You can see this energy gap between this X and the transition state of our normal process are very small. In most cases, there is the high probability to our molecule to drop from this place to this place, because it's a very tiny energy gap, right? Every molecule just need to get more stabilized by releasing energy. So instead of obtaining more energy and follows this path, this our reactive intermediate, so our molecule prefers to lower its energy and get stabilized through this pathway. So it's like either going through this path or this path. This is basically gaining energy and getting destabilized. This is basically removing energy and getting stabilized. So I hope the decision is much more obvious, right? Every molecule in our universe would like to get stabilized by releasing energy. So this particular X molecule will definitely choose this path to get stabilized. Now we are on this particular position. Okay, now our molecule can either go back to this place or go back to here. So this is the process. After the reactive intermediates, we go to the transition state. Okay, here this is this transition state. We go to the transition state. Then after that, we have two possibilities to obtain either cis product as initial, or we have the trans product. This is the process when photochemistry get involved in our isomerization process. You can see, instead of overcoming this huge energy barrier delta E1, we can irradiate our samples through photochemistry and overcome this small energy barrier to obtain the reactive intermediates, and then we stabilized it by jump down to the ground state mechanism, and then easily you can choose either go to the cis or trans. This is the things you need to know about the isomerization based on the photochemistry. I hope you understand this. If you have any problem, please feel free to comment below. I will try my best to explain it to you. In our next video, we will continue our discussion about the photochemistry.